Okay, so for our third talk of the session, actually our next two talks are going to be focused on the Lean Theorem Prover. And so the first talk in the Lean part is going to be Alena Gusakov, who's a PhD student in computer science at University of Waterloo. So Alena, please take it away.
Hi, everyone. So I'm going to talk to you today about the development of the combinatorics library in Lean. So developing a mathematical theory in a proof assistant is not the easiest task because you have to first select a way of expressing it in the logical framework that you're using. So you could be using dependent type theory, you could be using ZFC, and then once you select a way of defining it, then you have to figure out how to properly implement it in the language of the proof assistant that you're using. And this leads to a lot of discussion in the community surrounding these proof assistants on the best way to define things, how to set up lemmas, how to whether to bundle or not bundle definitions, which is like you include the properties in the definitions or do you list them separately, and then it's a whole thing. And it leads to some interesting conversations. So I'm going to talk to you about formalizing math. What is it and why do we care? I'm going to give a quick overview of dependent type theory, which is the logical framework that Lean uses. And then I'm going to talk about the Lean algebra hierarchy. So the Lean algebra hierarchy was one of the first sort of hierarchies that was developed in Lean. And then I'm going to talk about the graph theory library and why. So we use the algebra hierarchy at first as sort of a template for how to set up a lot of our definitions in graph theory. And I'll explain why it doesn't really work. So formalizing math, formalizing mathematical theory is the process of expressing it precisely in a logical framework, usually a proof assistant. Why do we do it? We do it for many reasons. So Kevin Buzzard has a blog post that talks about why we want to formalize. So we want to have like an indexed searchable database of mathematical results that all have a similar syntax. It's easy to find results that you're looking for. You want to find new insights about the theory that you're formalizing. So in the process of formalization, often people will find new ways of expressing a proof or new ways of writing definitions. And the kind of an interesting reason why we want to formalize is that we can find mistakes in our proofs. So there is a pretty big, like a pretty famous instance of this where we had two contradictory accepted papers to the Annals of Math, and then one of them got retracted after like several years. Kevin Buzzard talks about it in his blog post. I'm sorry, I don't remember the exact topic off the top of my head. A more recent example is Terry Tao, who led a team in formalizing the proof of the PFR conjecture in November of 2023, and found a mistake in one of the lemmas in his proof, which was corrected in the formalization, and he writes about it on his blog and kind of describes it in detail. So what is dependent type theory? Dependent type theory is a grammar for expressing mathematical statements. Everything in dependent type theory is a term or a type, and every term has a unique type. So the unique type part is important. So I threw together this diagram this morning. Please admire it. I'm very proud of it. So this diagram kind of shows the relationship between types, subtypes, and sets, which we have defined in Lean. So if we have a type, so we'll say V is the name of the type. Oh, let me give some examples first. So the syntax that we use for expressing that something is a certain type is term : type. So some examples of this include like 3 has type natural number, pi has type real number, etc. So everything that we're working with is going to be some term belonging to some type. So if we have this type v, so we express that something is of type v, like A is of type v with A colon v, and then we have sets defined in types. So the definition of a set is going to be v to prop, where prop is the type of provable statements, essentially. So, and I have it kind of included up there, sort of. I'm being a little bit hand wavy with this. But basically, a set in Lean is going to be a map from a type to a prop. And this is essentially saying that something of this type either belongs to the set or doesn't belong to the set. So if we have something, some term x belonging to the type, and we know that x is an element of set S, so we have prop hx saying that x is an element of S, then we have something called a type coercion from the set to a new type, where S, instead of being treated as a set belonging to a type, is now being treated as a new type. And we denote it with this arrow, this up arrow that we put before S. So we can convert something of type V with a proposition that it belongs to the set into something that is of type S coerced to a type. And we do this using the subtype.make coercion. And it's essentially pairing together the value from the type with the proposition. And then vice versa, if we have something belonging to this type, so y is of type S, then we can coerce it back to an object of type V by taking the first value of that term. And we have y.1 has type V, and y.2 has type y.1 is contained in S. So if we're defining graphs in mathlib, the first definitions that were added to mathlib were simple graphs. And the question we want to ask is, do we want to treat the vertices of a graph as a type or a set? So originally, the people that wrote the simple graph hierarchy decided to model it after the algebra hierarchy. So we first look at the algebra hierarchy to see how it's structured. So in the mathlib algebra hierarchy, algebraic objects, so groups, rings, semigroups, etc., are classes defined on a type. So when we have them defined on a type, we can easily express statements without type coercions or having to worry about carrying around the proposition that the object belongs to the set. So if we're just saying, A is of type V, et cetera, we don't have to worry about it belonging to a set if we're just talking about a group. This also allows us to take advantage of something called ad hoc polymorphism, which is essentially the dependent type theory equivalent of inheritance of properties. So when we're talking about algebraic objects, we have that rings are groups with some additional structure, right? We're inheriting properties, and we have like a hierarchy of objects that are inheriting properties from each other. So we want to use this version of polymorphism to essentially have this inheritance automatically. So that's algebraic objects. So now we want to talk about algebraic sub-objects. So subgroups, subrings, submodules, etc. In Lean, the sub-objects are defined on sets. The reason for this is that type coercions, so moving between types, always comes with an additional proposition that it will belong to the type, essentially. So in this case, if S is being converted into a type, we have the proposition that the element belongs to the set. We can define any arbitrary types from using any properties. So if we have, like, the real numbers, we can say we have a subtype. I forget the notation off the top of my head, but it's something like X type R, such that like X is less than or equal to 3, for example. We can define a subtype like this. So anytime we are working with subtypes, we're going to have to carry around this proposition, whatever it is, which can be a little bit unwieldy. So we want to avoid dealing with this type coercion by using the set construction. So instead of having it be part of the type, we have it be a separate proposition that we kind of keep track of. So this is the group definition. So group is defined on a type, and this is kind of a simplification. I have a couple of typos here because I was like copying and pasting from different parts of the hierarchy, because the definition of group inherits a bunch of things from other objects. So we have like semigroups and stuff like that. But basically, so binary op is supposed to be G to G to G, and it's like a right associative function. So it's taking in 2 elements and giving a new element. And similar for the other appearances of alpha and M up here. But basically, we have a binary operation, we have associativity, we have an identity element, and we have inverses. Then we have subgroups defined on a set. So instead of having it be defined on just a type, where we have to define some sort of type coercion, or a subtype where we have this sort of thing going on, also a type coercion. We have our carrier set, and we have the requirement that if we have our closure requirement, so if A and B are contained in the carrier set, then A times B is contained in the carrier set, and then everything else is kind of easy to keep track of. We don't have type coercions really. We have, 1 is contained in the carrier set. We have inverses are contained in the carrier set. So essentially, this is set up so that we can avoid type coercions, because type coercions make things a little bit difficult. For example, if you have 2 things that are of different types, you won't be able to compare them via equality. So if you have like 3 as a natural number, and we'll say like 3 as an integer, Lean has to perform a type coercion between these 2. So if you have 2 things that are different types, you can't easily compare them, and Lean will either have to do some kind of implicit type coercion, or you'll have to provide an instance that allows you to do that type coercion. So why do we want to use the group or the algebraic hierarchy as like a template for our graph theory hierarchy? Some similarities are that both are going to be structures that are defined on some set or some type, where we have, in the case of groups, we have a binary operation. In the case of graphs, we have a binary relation. When we're talking about sub-objects, so subgroups versus subgraphs, we have that both are going to be structures defined on subsets of the parent object. So in the case of subgroups, the subgroups set is going to be a subset of the group set. In the case of subgraphs, we'll have it be a subset of the vertices and a subset of the edges. And then both substructures are going to be, they're going to have certain properties that they inherit, and then certain properties that we impose. So with subgroups, they inherit the binary operation, and they must be closed under the binary operation, and also contain inverses and the identity element. And it'll also, subgroups will also inherit associativity. And then subgraphs are going to be subsets of the binary relation, kind of hand waving a little bit, which must still be symmetric and will inherit, for example, irreflexivity in the case of simple graphs or loopless graphs. Some differences between subgroups and subgraphs, or groups and graphs, are when we're talking about algebraic objects, we have that sort of hierarchy where, for example, as I mentioned, rings will build on the definition of groups. And we want this because, or we want to take advantage of this in our implementation. However, on the other hand, graphs don't have a hierarchy. For example, we can think of an undirected graph as a map from a digraph to, or we can think of undirected graphs as digraphs where we just forget the edge orientation, or we can think of we can think of digraphs as undirected graphs where we induce or we add edge orientations for every single edge. What we do with groups when we're proving things about them, when we're working with them, is often very different from what we do with graphs. And I'll talk more about this in this talk. That's the subject of the talk. Okay, so simple graphs in mathlib. So they were the first sort of definitions that we had. The simple graph hierarchy, as I mentioned, was designed to imitate that of the algebra library. Because if we're, as I've mentioned with the algebra library, it's easier to work directly with types or terms in the type as opposed to dealing with sets. So simple graph is defined as a symmetric irreflexive adjacency relation on a vertex type V. And then if G is a simple graph, we define subgraph G as an adjacency relation on the vertex type. This is a typo. It should be vertex type V with carrier set with type set V. We also have an is subgroup predicate for simple graphs, but that doesn't really get used because the is subgroup predicate says, if we have G is simple graph V and like H is simple graph, I'll just abbreviate it here, then I'll say like W, then V is a subgraph of W if there's adjacency between two vertices in V, only if there's adjacency between two vertices in H. I don't remember if it's distinct types. Might be the same type. I apologize. No one really uses it. That's why I don't remember the how it's implemented. So the definition of simple graph and subgraph is here. So we have adjacency between terms in V, and this adjacency relation is symmetric and loopless. And then subgraphs are defined on simple graphs. So they take in simple graph as a argument. And we have our carrier set of vertices. We have our adjacency relation between objects of type V. And then we have the requirement that two vertices in the subgraph are adjacent only if they're adjacent in the parent graph. We also have two vertices are going to be adjacent only if they belong to the carrier set. They're adjacent in the subgraph if they belong to the carrier set. We also have symmetry. That's a tactic that'll automatically try to look for a proof. Okay, so the simple graph definition has some nice properties. So much like the group definition that we were talking about, it's easy to work with terms of the type directly. So we have the nice sort of notation g.adj vw, and it's nice to construct things like edge sets, and it's good. Like it's fairly good to it's expressive enough for us to be able to do a lot with it. There's a okay, but there's one significant drawback. It's fairly difficult to work with common graph operations, substructures, etc. So one common graph operation where we run into problems is vertex deletion. So for example, if we have a simple graph defined on vertex type V, and we have some vertex V, and say we want to delete it from the graph. We can do this in two ways. We can define the deletion as outputting a new simple graph, where the new vertex type is a type derived from the original vertex type. So we construct like a subtype, and then we define the new simple graph as a simple graph on this subtype. Or alternatively, we pass in the new set, and then it gets coerced to a type. Or we can output a subgraph. So instead of outputting a simple graph, we just say this vertex deletion operation gives us a subgraph. And so in both cases, we end up having to perform type coercions. So in the first case, we're constructing a new type that is going to have a type coercion built in, but having to do that type coercion every time we want to talk about vertex deletion is going to introduce a lot of overhead. If we use the subgraph implementation instead, this will require us to coerce subgraph G into type simple graph every single time we want to use any simple graph lemmas. Or we're going to have to redefine all of our lemmas for subgraphs, which results in a lot of code duplication, which we want to avoid. Another example is walks in simple graphs. So walks are defined inductively. So we have our empty walk, and we have our sort of consecutive thing that takes in proof of adjacency and an existing walk, and allows us to append an edge to the beginning of the walk. So if we want to define walks in a subgraph, we'll have two options. We can coerce subgraphs to simple graphs every time we want to use walk, because one thing that's going on here is this g.adj is saying that we're using the adjacency relation of some simple graph. So this walk definition implicitly uses the simple graph as an implicit parameter. So either we're going to coerce subgraphs to simple graphs every time we want to use walk. This can happen automatically because we have type coercion already defined, but this will introduce a lot of this will introduce some type coercions for the graph specifically. Or we make a new walk definition for subgraph along with new lemmas and additional definitions. And this, again, introduces either code duplication or a lot of overhead. So regardless of what we do, we end up having to deal with either unnecessary type coercions that get in the way of things, or code duplication, or both. And this might indicate that our definitions need some improvement. So the key observation here is that in graph theory, every possible subobject is a graph. So any combination of a subset of the vertex set and a subset of the edge set is still going to give us some kind of graph, right? So if we have some graph that we're working with, we might consider like a cycle, and then we might say, okay, delete this edge from the cycle, and then we have some vertex here, and then we say, okay, delete this vertex, only focus on like this subgraph or whatever, delete this vertex from this cycle, etc. So we're constantly like adding, deleting vertices, and constructing new graphs essentially when we're reasoning about graphs. On the other hand, deleting an element of a group gives us something that's not typically a group. So if we look back at our relationship between types and sets, our original decision was, okay, we're going to require that graphs be defined on a type, and then subgraphs be defined on a subset. And then if we deal with type coercions along the way, oh well, it gets annoying. It's not great. So what we are led to is the conclusion that if we want to avoid these sort of type coercions and these sorts of problems with, for example, type equality, where if things are distinct types, you can't compare them, we are led to the conclusion that it's better to work with sets belonging to ambient types as opposed to imitating the algebra hierarchy with objects on types and subobjects on sets. So, for example, because we have distinct types not being equal, if we have like a simple graph defined on some like vertex deletion type, like subtype, and we have simple graph defined on some other type that we know is going to be equal, like it's the same type, we won't be able to say that they're equal because this essentially doesn't match up. Okay. So yeah, so this brings us to Peter Nelson's recent addition to mathlib, which defines multigraphs as having a vertex set and an edge set, and all required conditions placed on those. And we essentially keep track of the proposition that an object will belong to the set sort of automatically, or at least that's the goal. And this idea comes from an observation about working with matroids in Lean, which we run into the same thing. So yeah, thank you.